second session of Lightning Talks. My name is Martha Kim, and I'm a computer architect and co-chair of the Systems for Data-Driven Science Center at the DSI. In this session, you will hear from 4 expert presentations on the advances in core methods in data science. Before we begin, I'd like to relate the systems and the methods using our director Jeanette Wing's definition of data science, which is data science is extracting value from data. The methods that you will hear about are value extraction techniques, reasoning about the data, inferring causal relationships, and so on. The part that is implicit in all of this work is the computing infrastructure that supports these methods, by which I mean resources needed for real-world deployments, storage media, compute and network bandwidth, and of course electricity. Depending on the system, these resources may be used efficiently or may be wasted. We just heard about unpicked strawberries and empty trucks. Here we're talking about empty hard disks and idle servers. So the value that Jeanette mentions in her definition is actually the net of 2 sides of a balance sheet. The raw value extracted from the data, less the cost of the resources needed to extract it. So with this introduction, I'd like to turn the microphone over to our first speaker. This is Assistant Professor of Statistics, Samory Kpotufe.
Thank you for the introduction. I'll be talking about so-called transfer learning, domain adaptation. So first I'll try to give a generic sense of what the problem is. So imagine teaching a child to draw. Then they can quickly learn to paint. So somehow humans are able to transfer information from a particular task to another task with just very few observations of the next task. The next task, we'll call it the target task. So the key question is, can we teach machines somehow to transfer information in the same way humans or biological organisms do? So this general problem is called transfer learning or domain adaptation. And it's well motivated by current realities within machine learning. So in particular, most of you know that machine learning right now requires a lot of representative data. And what do I mean by representative data? I'll use this simple cartoon. So imagine we draw data from a particular source. Then we expect to do from the source can be a population from which of a particular object from which we're drawing. Then we can do fairly well with respect to that population from which we drew, because the data we drew is representative of that population. But now imagine that we actually want to do well with respect to a different population that is somewhat related, very close to the population from which we drew the data. Can we do this? Just the same way humans can transfer knowledge from a problem to another. So this is a problem of current interest, and we are sort of interested in the principles behind it. What are principled approaches? So here, let me give some simple examples. The key problem here is that representative data, perfect data is expensive. It's hard to obtain. So for instance, in computer vision, we have a lot of images that are fairly representative of particular subpopulations, but not necessarily representative of all given subpopulations of interest, target populations in a particular application. So this leads to well-known racial and gender bias in vision software. It's not limited to any given software. I'm giving the example of Microsoft Vision here, but it could be any of the softwares actually suffer these problems. The problem is fairly general. It occurs in a lot of applications. For example, Apple Siri's voice assistant, when it originally came out, it was trained on mostly American English speakers and could not understand, for instance, Scottish accent up till a couple years ago. So this is quite expensive, and it will be expensive for Apple. The usual solution is retrain, get a lot more representative data and retrain, and that's quite expensive. So here's another example, AI in judicial systems. The usual data is biased towards prison inmates, and doesn't do that well. And the predictive softwares don't do that well on more general populations. And this can be quite expensive. in a lot of the emerging applications, for instance, in medicine, in Internet of Things, the not having representative data, but wanting to use other data sources as sources of imperfect data to do well, leverage sources of imperfect data to try and do well on particular target data without having to necessarily acquire perfect data. So that's sort of the key problem. So what are the fundamental research questions here? So for instance, the basic question is, what algorithms can we develop to transfer well? There are tons of algorithms out there already, various heuristics that do well in particular situations, but we are interested in principles. What are the main principles in transferring, leveraging a source of imperfect data to do well on some other target data? So you can imagine that these various heuristics are sort of based on the amount of information you have in the imperfect data, in the source data about the target problem. What information do you have about the target problem? How can you measure such information? And we don't even know what we mean here necessarily by information or distance between data sources, distance between the source population and the target population. So those are sort of the fundamental questions, trying to understand and classify, categorize heuristics in terms of those that are good for transfer, those that are not very good for transfer, and understand how to measure transfer, how to measure transferability. So I'll talk about these notions of distance for a second, because distance is sort of the most important. Distance between distributions or between populations is sort of the most important thing that researchers or theoretical researchers in the field have been trying to capture. And so the main challenge here is the following. Imagine just trying to capture a simple notion of distance, the distance between two cities, Nairobi to Mombasa. That would sort of depend very much on how you intend to get there. So are you intending to fly there? Are you intending to take the train or go by car? And similarly, the notions of distance that are important here in transfer depend very much on the particular machine learning application, whether it's classification, regression, clustering, and it depends very much also on the actual set of algorithms you're trying to use. So you're trying to use neural networks, random forests, and such. And so I hope I'm giving a sense of what the difficulty is here. We have to sort of try and come up with notions of distance that capture the essence of transfer learning. So we've been gaining various mathematical insights on this question. I mean, by we, the whole field, myself included. And these insights are sort of based in statistics and information theory. So I'll sort of stop here and thank you for attending.